Welcome to Module 2 of Computer Application in Chemical Engineering 2. In this module, we move from theory to practice. We will explore process modeling, process simulation, optimization, and the use of software tools such as MATLAB, Excel, and process simulators like Aspen+. Section 1. Process modeling. Modeling is the representation of a real system with mathematical equations. Purpose: to predict the performance of chemical processes under different conditions. Steps in modeling: define the system boundaries, make simplifying assumptions, write material and energy balances, add constitutive relations such as thermodynamics and reaction kinetics, solve equations numerically. Types of models: steady-state models assume no change with time, used in equipment sizing and plant design. Dynamic models account for changes with time, used for control system design and safety analysis. Section 2. Process simulation. Simulation means using a computer program to solve the mathematical model of a process. Purpose: to study process performance without physically building the plant. Examples: simulating a distillation column to predict energy consumption and purity. Testing alternative reactor designs. Studying the effect of recycle streams in a plant. Advantages of simulation: saves cost and time, provides insight into complex interactions, allows testing of what-if scenarios safely. Section 3. Optimization in chemical engineering. Optimization means finding the best conditions to maximize or minimize a particular objective, such as profit, yield, or energy consumption. Steps in optimization: define the objective function, such as minimizing energy use. Identify constraints like material balances or equipment limits. Use mathematical methods to find optimal solutions. Applications: optimal reactor temperature for maximum conversion, minimizing energy in distillation, scheduling and resource allocation in plants. Computers allow engineers to solve optimization problems with multiple variables and constraints using techniques such as linear programming, nonlinear programming, and dynamic optimization. Section 4. Software tools in chemical engineering. Modern chemical engineers rely on specialized software for computation and simulation. MATLAB, excellent for numerical methods, solving equations, data analysis, and visualization. Widely used in academia and research. Excel, useful for quick calculations, regression analysis, and simple process models. Aspen+ and HYSYS, industrial process simulators for steady-state and dynamic simulations. They include extensive thermodynamic databases and equipment models. COMSOL Multiphysics, used for solving PDEs with finite element methods, particularly in transport phenomena and reactor modeling. Python, increasingly popular for open-source computation, with libraries for numerical methods, data handling, and visualization. Each tool has its strengths, and engineers choose based on the complexity of the problem and available resources. Section 5. Case studies. To make these concepts practical, let us consider a few examples. Case study 1. Distillation simulation. Using Aspen+, a student simulates a distillation column for separating ethanol and water. By adjusting reflux ratio and number of trays, the student identifies the most energy-efficient design. Case study 2. Reactor optimization. MATLAB is used to model a continuous stirred tank reactor with an exothermic reaction. The optimization routine finds the reactor temperature that maximizes conversion without exceeding safety limits. Case study 3. Wastewater treatment modeling. Using COMSOL, engineers simulate diffusion and reaction in a wastewater reactor. The model helps predict pollutant removal efficiency under different flow rates. These case studies highlight how computers transform theoretical concepts into practical engineering solutions. End of Module 2. This concludes Module 2. We have explored process modeling, simulation, optimization, and the use of software tools. We also looked at case studies that demonstrate how computer applications are used to design, analyze, and optimize real chemical engineering processes. In this course, Computer Application in Chemical Engineering 2, we divided our learning into two major parts. Module 1, the fundamentals of numerical and computational methods, including solving equations, ODEs, PDEs, and regression. Module 2, the application of these methods in process modeling, simulation, optimization, and the use of specialized software. Together, these modules provide both the mathematical foundations and the practical tools chemical engineers need to solve modern industrial problems. Mastery of these concepts will prepare you to design efficient, safe, and innovative chemical processes using computational methods.